Hello everyone, welcome back to this online class. Today we are going to look at the method of Laplace transform in solving partial differential equations. In particular, we are asked to solve the boundary and initial value problem given by our PDE is partial u partial x plus 2x partial u partial t is equal to 2x. This is defined for all x greater than 0 and t greater than 0. Our boundary condition at x is equals to 0 is 1 for all t greater than 0, and the initial condition at t is equals to 0 is also equals to 1 at x, or simply for all x greater than 0. So to solve this one, we are going to start by taking the Laplace transform on both sides of the given PDE, or simply operate with the transform operator on both sides of the given equation. So we are going to say, let L be the Laplace transform operator, Laplace transform operator. So now the first step 1, is to operate with L on both sides of the PDE. So when you operate with that transform operator, you're going to get the Laplace transform of partial u partial x plus the Laplace transform of 2x partial u partial t is equals to the Laplace transform of 2x. Remember, this operator, it is operating on the variable t. So we should say that let L be the Laplace transform operator which operates on the variable t, which operates on the variable t, not x. Remember, this is a PDE. U is a function of x and t, because the independent variables and x are x and t, while the dependent variable is u. So from here, u depends on x and t. So we are going to operate on the variable t. When you operate on the variable t, we transform it to a new variable s. X, we assume, is constant with respect to the Laplace transform operator. So now let's see. If x is constant, then this equation can now be written as, this implies that derivative with respect to x of the Laplace transform of u of xt plus 2x can now be factored out. Then now we talk of Laplace transform of partial u partial t is equals to, this is 2x, a constant, times the Laplace transform of 1. 1 times anything. Remember, 2x is the same as, take note, that 2x can be written as 2x multiplied by 1. So that now when you go to the Laplace transform table, it is easy to read these transforms. So I will also, before we say let, so this can be written as derivative with respect to x of the Laplace transform of u of xt plus 2x. Here we'll have s times the Laplace transform of u of xt minus u of x 0. Then plus, not plus, is equals to 2x. The transform of 1 is 1 over s. So that's 2x over x. The next thing we say let u bar, and let me write that in the second line. I can take this to the left. So let u bar is now a function of x and s be the Laplace transform of u of xt. Remember what I'm calling u bar. U bar is a function of x and s. Because now we have transformed the variable t to the new variable s. So u bar is the transform of u. So this equation can now be written as du bar dx plus 2x. Here we have s times u bar minus u of x0 is equals to 2x over s. Step 2, you apply the initial condition. So we are going to write step 2. Apply the initial condition. What are we told? That u of x when time is 0 should be equal to 1. So we are told u of x0 is equals to 1, which we have here. So this value here will be equal to 1. Excuse me. So therefore, that equation can now be written as, so with this initial condition, our equation can now be written as du bar dx plus 2x into s u bar minus 1 is equals to 2x over s. Or I can open the bracket du bar dx plus 2x s u bar minus 2x is equals to 2x over s. Or if I rearrange it, I'm going to get du bar dx plus 2x s u bar is equals to 2x over s plus 2x. Look at the right hand side, 2x is common. That can be factored out. So that we are going to get it right, or du bar dx plus 2x s u bar is equals to 2x outside into 1 over s plus 1. That's what we have. Now look at this equation. This equation is a linear ODE in the dependent variable u bar. Linear ODE in the dependent variable u bar. And how do we solve such kind of equations? We use integrating factor methods. So when finding the integrating factor, I'm going to integrate the coefficient of u bar. This is our p of x. This one is our p of x, which you need to integrate. Remember, integrating factor is given by exponential of the integral of p of x dx. That's how we define the integrating factor. And now in this case, our p of x is 2x s. Let's integrate that with respect to x. So you can say integrating factor, if denotes integrating factor, is exponential the integral of p of x dx, which is equals to exponential integral of 2x s dx, which you will get exponential 2 times x squared over 2 times s. You will integrate x. And when you simplify this, will give you exponential. Because the 2 will cancel with this other 2. So it is x squared s. X squared s. That's what we have. Now, multiply the ODE by the integrating factor to get multiply the ODE by the integrating factor to get, because we are multiplying both sides of that equation, so we are going to get exponential x squared s du bar dx plus 2x s exponential x squared s u bar is equals to 2x into 1 over s plus 1 exponential x squared s. Look at the left-hand side of this equation. That can be grouped as derivative of the dependent variable and the integrating factor. Of course, derivative with respect to the independent variable. So this left-hand side, when you group it, it becomes derivative with respect to the independent variable. Our independent variable is x, of the product of dependent variable, which is u bar, and the integrating factor, which is exponential x squared s. That's the same, because if you work out that derivative, you go back to what we have up there. Here, I mean on the left-hand side of that equation. On the right-hand side, it remains the way it is, 2x, 1 over s, plus 1, exponential x squared s. Now, I want to cross multiply by dx. You write multiply by dx. Of course, on both sides, what are we going to get? It will be derivative of u bar exponential x squared s is equals to 2x. This is 1 over s plus 1 exponential x squared s. Then integrate. Remember, there will be a constant C of integration. So we multiply by dx and integrate. I told you integral and derivatives are inverses of each other. So this and this will cancel. So that on the left-hand side, we only remain with the u bar times exponential x squared s. So therefore, u bar exponential x squared s is equals to, look at 1 over s plus 1. That is a constant because here there's dx. Remember there was dx here because I was multiplying by dx. So take note. So you're integrating with respect to x. So anything that does not depend on x, you can factor that out. So we'll have 1 over s outside plus 1. The integral of 2x exponential x squared times s dx. So how do you integrate this? You are going to use u substitution But now I cannot use u because already we have the variable u. We can just say let z be equal to x squared s. So from here, we can get dz dx to be 2x s, or when you make dx the subject, dx here will now be equal to dz over 2x times s. So that's what we have. Now, when you substitute it here, what are we going to get? It will be equal to 1 over s plus 1, the integral of 2x exponential z dx is the same as dz over 2x times s. You see 2x will cancel with 2x. So this can as well be written as 1 over s plus 1, the integral of exponential z dz over s. And that 1 over s can be factored out. So we can now talk of 1 over s into 1 over s plus 1, the integral of exponential z dz, which can be written as 1 over s squared plus 1 over s exponential z. When you integrate exponential z, you get exponential z. Now replace z. We put z is x squared times s. So you have to replace z. Check how we defined our z. It was x squared times s. So that our solution here, but remember there's a constant c of integration. Don't forget the constant c. There's a constant c of integration. Never forget it. You are almost forgetting, but we have remembered. So usually, don't forget that constant of integration because this is indefinite integral. Now, when you replace z, we are going to have 1 over s squared plus 1 over s exponential x squared times s plus the constant c of integration. So on the left-hand side, we have u bar exponential x squared s. And then you make u bar the subject. Make u bar the subject. So what are we going to get? We are going to get u bar, needs another color. We're going to get u bar is equals to, we are dividing by exponential x squared times s. So that will give us 1 over s squared plus 1 over s plus c times exponential negative x squared s. I have divided that equation by exponential x squared s to get what I've written down there. So this is our Laplace transform. Now we need to get the function. So what you do is operate with L inverse on both sides. So the last step, that should be step 3. Even before you operate with L inverse on both sides, we need to know what is the value of C. So apply the boundary condition. Apply the boundary condition. Look at our boundary condition at x is equals to 0. u0t was equals to 1. So it is here that you need to get the Laplace transform on both sides, because you see our equation is in terms of the Laplace transform. So don't forget, when applying the boundary condition, you have know the Laplace transform of that boundary condition. For the initial condition, it will be easy to apply like you saw up there. So the transform of u of 0t is the same as Laplace transform of 1, which means Laplace transform of u of 0t is equals to 1 over s. What does it mean? That we substitute or we put x is equals to 0 and u bar is equals to 1 over s in, let's call this equation star. So write in equation star to get, let's make those substitutions. So we are going to get 1 over s is equals to 1 over s squared plus 1 over s plus c times exponential 0. Anything raised to 0 should be equal to 1. So that is c times 1, which I don't need to write. I don't need to write the 1. And so you see, this will cancel with this. So from here, you can make c the subject. It is equals to negative 1 over s squared. So therefore, let's substitute it into equation star. So therefore, our equation star will become, let me use another color. Our equation star now becomes u bar is equals to 1 over s squared plus 1 over s minus 1 over s squared exponential negative x squared times s. And so the last step is to find your solution, u of x t. So we'll write here step 4. Of course, this is what you're going to operate on. So this, what will give us our u of xt. So step 4. You now operate with L inverse on both sides of equation. Let's call it star star, the two stars. So we now operate on that equation star star using the L inverse operator. So take note here that we said u bar is the Laplace transform of u of xt. That's what we said. So therefore, if you operate with inverse on both sides, so L inverse of u bar will give us u of xt. So on that equation star, we are going to talk of L inverse of u bar is equals to L inverse of the right hand side, that is 1 over s squared plus 1 over s minus 1 over s squared exponential negative x squared times s. So that's what you get. And you see Laplace transform operator and even the inverse operator, they are linearity property. We're going to use the linearity property of those two operators to rewrite the right hand side of this equation. So here we are going to get u of xt is equals to L inverse of 1 over s squared plus L inverse of 1 over S minus L inverse. So the other one should be minus L inverse of 1 over S squared times exponential negative x squared S. So that's what we have. Now, to get the inverse, you need to refer to the Laplace transform table. The first two terms on the right-hand side is easy to know their inverses. So on the right-hand side, what is the inverse of 1 over S squared? That is t. It is the Laplace transform of t, which gave you 1 over S squared. What about the inverse of 1 over S? We are done with this. Now this other term is 1. When you transform 1, you get 1 over S. But now here, what will be the answer? So minus, the answer there is f of t minus a times h of t minus a. H there is the Heaviside function. Take note of the second shifting theorem. That's what I've used there. Second shifting theorem. I'll write here a note. This note is the second shifting theorem or property, second shifting property of Laplace transform. That if, let me use another color, it states that if, let me take this to the left so that I create a space there. If Laplace transform of f of t is equals to f of s, then the Laplace transform of f of t minus a times h of t minus a should be equal to f of s times exponential negative a times s. That is the second shifting property of Laplace transform. So now when you get the inverse, I will now assign this one to my f of s. And from here, it means that our a is equals to x squared. We are doing the comparison. Compare this. You see, when we now talk of inverse, so therefore from here, it means f of t minus a times h of t minus a is the same as L inverse of f of s times exponential negative a s. That's what we have. Now, if I put f of s is 1 over s squared, what is the inverse of 1 over s squared? So, L inverse of f of s is equals to, of course, our f of t is the L inverse of f of s, which is L inverse of 1 over s squared. And that should be equal to t. Our a is equals to x squared. So I need f of t minus a. So f of t minus a, that is simply equal to f of t minus x squared. And you see, f of t is t. So what is f of t minus x squared? That will simply be equal to t minus, where there is t, you put t minus x squared. We are replacing the t by t minus x squared. What about h of t minus a? H of t minus a is the same as h of t minus x squared. It is an arbitrary. It is the Heaviside function. You see, you know what we mean by Heaviside function. Let me draw it here. You can now go back to color blue. This Heaviside function will look like this. The t-axis, the h-axis. So if you have a here, then I have, let's say here I have 1. So that function is defined in this manner. Up to here, it is 1 to the right of a, and to the left of a, it is 0. It simply behaves like a switch that is off until t is equals to a, at which point it turns on. So that is the Heaviside function. So in this case, instead of a, we are now talking of x squared. So this way we have x squared. So to the left of x squared, the function is 0. And to the right of x squared, the function is 1. So coming back to our transform, now the answer here will be t plus 1 minus f of t minus a. We got t minus x squared. That's what we got. Then times h of t minus a, which we got h of t minus x squared. Could say there, or u of xt is equals to that. So what we have found here is the solution for our given PDE, which is subject to the boundary condition and the initial condition that was given. So this is our solution, and we have said our h is this Heaviside function. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at other problems in Laplace Transform. Bye-bye.